Okay.
And here's a laser pointer.
Okay, maybe I'll erase those. Oh, thank you. Thank you. I'd like to start by thanking the organizers for the invitation. So today I'll be speaking about joint works with some collaborators, Erwan Fao, Pierre Germain, and Laurent Thoman. I would like to continue the same direction that Nikolai has started, which is studying nonlinear dispersive equations in situations when there is a confinement that is either coming from the domain or from a confining potential. And the reason why this question is quite important is that if we think about it, as we all know, if we study this nonlinear dispersive equations on RD, then dispersion is a mechanism for non-dissipative decay. This means that at least at the linear level, you have that linear solutions decay in L infinity like t to the minus alpha for some alpha positive. And this decay is the reason behind all nonlinear asymptotic stability of equilibrium solutions on RD. By this I mean that starting from small, smooth initial data, then one can show that solution remains small in pretty much all sensible norms, and we can often describe the asymptotic behavior, at least when you have sufficient decay, which is typically linear scattering. However, this picture changes completely if you study nonlinear dispersive equations on compact domains. On compact domains, wave packets have no escape. The wave packet components of the solution have no escape from interacting indefinitely with each other. Particularly, there is no infinity for those wave packets to escape to. And as a result, dispersion does not translate into decay, neither at the linear nor at the nonlinear level. And this complicates things quite considerably. And the consequence of that is that you lose all asymptotic stability results of equilibrium solutions that we had on RD. And the only control that we can retain, the only global control that we can retain on the solution is the one that is coming from conserved quantities, which if your system is not integrable, they are very few. Then they are typically at the level of L2 or H1. And not only you lose the proof of the stability of those equilibrium solutions, you don't expect those equilibria to be stable in the long run. In particular, out of equilibrium dynamics is anticipated. And starting even from very, very small neighborhoods of the origin in your phase space, you can already observe many characteristically different behaviors, such as Km tori or several of the behaviors that we will be talking about today. And the main problematic here is how do we understand, explain, or capture this out-of-equilibrium dynamics. One main aspect of it is that of energy cascade. Energy cascade means that the energies of the system, while remaining conserved, they will move their concentration zones between characteristically different length scales. Let me explain this for the forward cascade of energy, which at least Nikolai was interested in as well. So the forward cascade of energy means that the energy will migrate from low frequency concentration zones to high frequency concentration zones. In physical space, this means that the energy will move from large scales to very small scales. So heuristically speaking, we are thinking of the solutions that Nikolai and we were interested in as solutions that are initially oscillate at scale order of 1, but at some later time, they start oscillating at much, much smaller length scales. And the main question is, how do we capture this cascade? Or more generally, how to understand the out-of-equilibrium dynamics? And as far as I know, there has been two approaches in the mathematics and physics communities in order to capture this or to answer this question. The first approach was based on the relation between the growth of Sobolev norms of solutions and the energy cascade phenomena. And this relation can be explained as follows. If we look at the definition of the Sobolev norm over here, suppose we are working on the torus TD for simplicity. Of course, it is nothing but the sum of all L2 norms of derivatives up to order alpha of u. But it will be more illuminating for us to look at its formulation in Fourier space over here. we look at this factor, 1 plus n squared to the s, this factor penalizes, obviously, high frequencies much more than it penalizes low frequencies. So if the energies of the system are moving towards high frequencies, then this has to be accompanied by this growth of suburb norms. And here many people contributed to this approach, starting from the pioneering works of Bourgain and Stafilani, who obtained bounds on the growth, as Nikolai explained at the beginning of his talk. There were also contributions of Cookson, Colliander, Kiel, Safinata, Roca, and Tao, myself, Schroedinger, Galosha, and Gardia, and then the result that there's also the result that Nikolai discussed. The second approach, which was, I would say, was more popular in the physics literature, is the effective dynamics approach. And it's based on the following idea. It's based on the idea that the long-time dynamics is extremely rich when you are working on a compact domain, that they have no chance of making uniform statements about the dynamics, about the long-term dynamics, let alone the asymptotic dynamics. So the next best thing to do is to try to find order in this chaos and try to identify certain regimes where you can say something about the long-term dynamics. And one way to do that is to derive effective equation for the dynamics in those regimes by taking various limits of your original system. We'll talk about some instances of this approach. Actually, this is the main subject of this talk. But I should say that the most well-known instance of it is a physical theory that goes by the name of wave or weak turbulence theory. The equations of wave turbulence have been written at least since the first part of the half century by Peierls and Hasselmans, but the theory was mostly invigorated by Zakharov and his students and collaborators and his school in general. There's also contributions of Newell, Maida, McLaughlin, Tabak. Of course, this list is non-exhaustive. It's very huge. Lucanen and Spohn, Escobar, Velasquez as well, and many others. Okay, so I trust Nikolai gave us a very nice introduction about the first approach. So I would like to talk about the second approach today, which is the effective dynamics approach. But before we start discussing those issues, let us fix the model equation on which we will base the analysis. And this is the same equation that Nikolai was considering. We'll consider it in 2D, cubic nonlinear Schrodinger equation, and we will consider it on a box of size L with periodic boundary conditions. So the equation is over here. The solutions, we won't be interested in the existence questions of the solution, but all solutions we'll be talking about exist globally in time, at least if you restrict for small L2 mass. By the way, L2 is a conserved quantity for this equation. And this is something that was proved by Bourgain in 1993. The sign of the nonlinearity won't be of importance to us, partly because we are restricting to such small solutions. And indeed, our aim is to understand the out-of-equilibrium dynamics of such small solutions. And for this, we will adopt the ansatz V is equal to epsilon u and think of u as having size 1 in L2 norm in order to emphasize the size of solution. And the only difference this makes is that you have an epsilon squared term on the right-hand side of the equation. So as we said, we are interested in the frequency dynamics of solutions. So we'll be interested in how this equation looks like in Fourier space, which is something that also Nikolai went over. So what we'll do is that we'll expand U in terms of its Fourier series. We'll write it as 1 over L squared, the sum over K in Z2 over L. Since we are working on a box of size L, Z2 over L is our Pointryagin-Newell. And Ck is nothing but the Fourier transform of U. So if you take the Fourier transform of the equation, this is ID to U, this is the Fourier transform of the Laplacian, and this is the Fourier transform of the nonlinearity written as a convolution. So here the sum is over K1 minus K2 plus K is equal, plus K3 is equal to K. If you look at this equation, you notice that the linear dynamics is much faster than the nonlinear dynamics on the right-hand side. So we do the natural step, which is called the interaction representation step. This means that we will conjugate by this linear flow, define ak of t to be e to the 4 pi squared I k squared t multiplied by ck. And in those coordinates, the equation satisfied by AK is essentially the same as that of CK, except that you have removed this linear factor at the expense of introducing this very important time oscillating factor, e to the minus 4 pi squared I omega t, where omega is k1 squared minus k2 squared plus k3 squared minus k squared. So if we look at this equation, it tells us that NLS can be written in Fourier space as an infinite system of ODEs. And this infinite system of ODEs tells us how the frequency mode at AK is being excited by the frequency modes at K1, K2, and K3 in the set S of k. Of all those interactions and excitations, we've already seen from the previous talk that there stands out to be a particularly important family of interactions, which is the family of resonant interactions, and these correspond exactly to the triplets k1, k2, and k3 in S of k, for which capital omega is equal to 0. And we will see that those interactions play a particularly important role in deciding the long-term dynamics. So this motivates us to define the resonant linear Schrodinger system, which is the same as the nonlinear Schrodinger equation, except that you restrict this sum over R of k, which corresponds to omega equals 0. So this drops. Okay, so these are the two equations that we'll be interested in for most of this talk. Okay, so let me start by talking about the effective dynamics approach. And before I go into talking about the recent progress on that approach, let me talk about the most well-known instance of it, which is the theory of wave turbulence. The theory of wave turbulence, it seeks to give a statistical description of the out-of-equilibrium dynamics for nonlinear dispersive equations, and it was mostly invigorated by Zakharov in the 60s, who was trying to find an analog of Kolmogorov's theory of hydrodynamic turbulence. And the setup, or one of the setups that you would find in the physics literature, is that you start with initial data for the nonlinear Schrodinger system that is given by random variables. So each ak, the frequency mode ak at time 0, is given by an independent random variable for k in Z2 sub L. And the key quantity to which you would like to understand its dynamics is the so-called wave spectrum, and it's defined as the expectation of ak of t squared. So you start with ak at time 0 to be random, you solve the NLS equation, and then you take the expectation of absolute value of ak squared. Again, as we said, the guiding philosophy of this theory is that to find effective equations for n of k by taking various limits of your original system. And if you look at the physics literature into the limits that are done in order to find the effective equation for n of k, these could be split into three types of limits. The first type is the statistical and time averaging step. Here I should haste to point out that this is particularly non-rigorous step. The second type of limit that is done is the large box limit. So you start with the NLS on box of size L, and then you let L go to infinity. Oh, sorry. So the k variable that used to be in Z2 sub L becomes a continuous parameter in R2. And the last type of limit that is done is the weak nonlinear limit, which essentially entails ignoring some higher order terms in a multiple time scale expansion in epsilon, which is the size of the data. Again, okay, so all this derivation is not rigorous, and it's far from being rigorous at this point. But if you do it, this gives an effective equation for the wave spectrum n of kt, which is actually quite important in applications. And this is called the wave kinetic equation, or sometimes called the Kolmogorov-Zakharov equation. And as we said, it was derived much earlier than Zakharov. I won't be using it, but just for your curiosity, I write it on this slide. So once you have this equation, you start asking what does it tell you about the long time or not out of equilibrium dynamics of the nonlinear Schrodinger equation. And indeed, it actually tells you a lot. It tells you surprisingly interesting statements, even from the point of view of non-equilibrium statistical mechanics, especially in terms of its stationary solutions, which are called spectra. And those spectra can be split into two groups. There are spectra that correspond to thermodynamic equilibria, or for example, translate to Gibbs measures. And for example, the Rayleigh-Jeans spectrum, which is given by n of k equals k to the minus 2. You can obviously see that this is a trivial solution of this. If you plug n of k equals k to the minus 2, you get k1 squared minus k2 squared plus k3 squared minus k squared, and this is killed by the delta function over here. But this is not the interesting solution of this equation. The interesting solutions were actually derived by Zakharov, and they carry his name. These correspond to non-equilibrium stationary solutions. And one of them is a direct cascade spectrum and an inverse cascade spectrum. Let me talk about the direct cascade spectrum. It corresponds to the existence of a statistically steady state where the energy is being pumped at a constant rate from low frequencies towards high frequencies. So it is actually a very strong statement. However, the main caveat of this theory is that it is not rigorously justified. This rigorous justification is not only interesting as a mathematical statement, it's actually quite interesting from the physical point of view. For reasons that I don't want to go into today. So instead, motivated by this question, what we will do is that we will dispense. Sorry. Okay, we will dispense of the statistical and time averaging step, but we will still take the large box limit and the weak nonlinearity limit. And yes, there should be an epsilon to the 4 over here. Yeah. To the 4, yeah. And this is very important. That it's one of the problems in this theory is that epsilon to the 4 is a very long time scale. And you start observing this. Excuse me? Yeah, this is the first term that, yeah. Yes. Yes. But indeed, in reality, you start observing this at a much earlier time scale, which is still not understood even in the physics community. Okay, so motivated by all those questions, what we did with, in collaboration with Erwan Fau and Pierre Germain, we dispensed of this averaging step, but we still took the large box limit and the weak nonlinearity limit, and we will see that only just by taking those two limits, we will get some interesting conclusions. Okay, so this allows us, this is what we'll do. This will give us an effective equation for a.k.a. of t instead of an effective equation for the spectrum absolute value of a.k.a. squared. And we will see that the effective equation indeed approximates the analysis dynamics in certain regimes. But, okay, so I motivated the large box limit and the weak nonlinearity limit by, from the perspective of wave turbulence theory, but these are two limits that are interesting in their own rights, and they can motivate it independently. For example, the large box limit or the infinite volume approximation is based on the idea that a physical system might be more effectively modeled by an equation on RD than by an equation on a box of size L. So if you have a physical system that is modeled by NLS on a box of size L, it might be more effective to model by NLS on R2. But however, this approximation has its limitations, and it is limited to initial data and time scale for which the solution does not feel the difference between the box of size L and all of R2. So how do we decide whether the solution feels the difference between the box of size L and all of R2? There's a very nice back of the envelope calculation that is quite illuminating here. So if this is the box of size L, which could stand for your laboratory or the ocean, and if you take an initial data that is well localized both in physical and frequency space, so it's localized, say, at frequencies order of 1, and we'll take this data to have size epsilon. Then there are two relevant time scales for such initial data. The first time scale is the time for this bump to hit the boundary. So this is a wave packet that is localized at frequency order of 1. For NLS, such wave packets travel at speed order of 1 as well. So at least heuristically, it will take this bump a time order of L, in order to see the boundary, in order to feel that it is on a box, in a finite box, the finite size effects. So this, I would call this T1. The other important time scale for such initial data is the nonlinear time scale. This is the data of size epsilon. The nonlinear time scale is 1 over epsilon squared. Epsilon to the minus 2. And the reason for that, if you remember the right-hand side of the equation, at least schematically, it looks like this. IDTF is equal to, or IDTU was equal to epsilon squared, the nonlinearity. So if we integrate this over a time interval that is strictly less than 1 over epsilon squared, this nonlinearity essentially plays no effect. Okay, so, and this is usually a good approximation for a cubic equation. The nonlinear time scale is epsilon to the minus 2. So now all we have to do is compare those two time scales. If the first time scale, T1, is much larger than the nonlinear time scale, which means that if L is much bigger than epsilon to the minus 2, then the equation will start, the solution will start behave nonlinearly before even feeling that it is in a finite box. And in this, we can use NLS on R2 very safely as a large box approximation. However, if T1 is much less than the nonlinear time scale, or if L is much less than epsilon to the minus 2, then this wave will hit the boundary, or will feel that the effect of the boundary even before the nonlinearity kicks in. In particular, NLS on R2 is completely irrelevant in this regime. And we will be interested exactly in this weakly nonlinear regime. It's weakly nonlinear because, as you can see, epsilon is less than negative power of L. And we will see that in this regime, a new equation dictates the nonlinear dynamics of NLS. So let us start by formally deriving this equation. So first, allow me to argue like a physicist and not care a lot about how the convergence issues. So let me argue formally in order to derive the equation, and then we'll make it rigorous. So the first formal step that we will take, so we'll start with the equation, considering the equation for ak of t, the NLS equation for ak of t. The first approximation I will make is that because the data is small enough, I will pretend that the equation satisfied by ak of t is exactly the resonant nonlinear Schroedinger equation. So I will, instead of summing over all triplets k1, k2, k3, such that k1 minus k2 plus k3 is equal to k, I will only take this sum over the resonant interactions R of k, for which omega is equal to 0. Of course, this is a big approximation that needs to be justified later, but we'll do that later, as we said. So the next thing that we would like to do is we would like to take L go to infinity. This means we would like to regard this sum as a Riemann sum and replace it by an integral. However, if you notice, you directly notice that this is not a regular Riemann sum because there's a nonlinear lattice relationship, omega equals 0, involved in defining it. So before I can take the limit L go to infinity, I need to reparameterize the sum in a favorable way. And this is what we will do next. So first, I will do a very simple change of variables. So for k1, k2, and k3 in R of k, we will define n1 such that k is equal to k1 minus k, n2 to be equal to k2 minus k, and n3 to be equal to k3 minus k. Then the first relationship over here translates into saying that n2 is equal to n1 plus n3. And the second relationship, omega equals 0, translates into saying that n2 squared is equal to n1 squared plus n3 squared. It's a very easy computation. This means that n1 plus n3 squared is equal to n1 squared plus n3 squared, which is equivalent to saying that n1 is perpendicular to n3. So I can rewrite this sum in the variables n1 and n3 as follows. So it's the sum over n1 and n3 in z2 sub L, such that n1 is perpendicular to n3, ak plus n1, which used to be k1 in the old variables, ak plus n1 plus n3, which used to be k2 in the old variables, and ak plus n3, which used to be k3 in the old variables. I still cannot take the large box limit of this sum, so we need to parameterize it further. And for this, I will factor out the greatest common divisor out of the coordinates of n1 and n3. So we'll write n1 is equal to alpha pq over L, where alpha is an integer and pq are in z2 are relatively prime. If moment's thought tells you if n1 is of this form, and if n3 is perpendicular to n1, then n3 has to be of the form beta minus qp over L, where beta is an integer and minus qp is the rotation of pq by angle 90 degrees. Now, a lattice point of the form pq over L is a special lattice point, and it's called a visible lattice point. The reason why it's called visible is actually quite simple. So if you draw the lattice z2 sub L, or any lattice for that matter, then a point j is visible if and only if the segment oj does not intersect any other lattice point in z2 sub L. In particular, j is visible from O with an unobstructed view from the other points of the lattice. So what we did is that we write n1 is equal to alpha j, where j is visible, and n3 is equal to beta j perp, where beta is an integer and j perp is the rotation of j by 90 degrees. So this allows us to write this sum as in terms of alpha, beta, and j as follows. So we have a sum over alpha and beta, the sum over j in z2 sub L visible, ak plus alpha j, which used to be n1 in the old variables, ak plus beta j perp, which used to be n3 in the old variables, and a bar at k plus alpha j plus beta j perp, which used to be n2 in the old variables. Now we are in a much better position to pass to the large box limit, which amounts to replacing those sums by an integrals. But the only caveat is that if this was a sum over all lattice points, then it's very easy to change it into an integral. This is Riemann integration. But this sum is not a sum over all lattice points. It's only a sum over visible lattice points. So before we can transform it into an integral, at least even at a formal level, we need information about the equidistribution of visible lattice points, and we need to obtain quantitative error estimates on that. So this is what I would like to explain on this slide. What we mean by equidistribution is that if you give me a very nice function, sufficiently nice function u, and you take L to the minus 2 times the sum over k in z2 sub L u of k, then this will converge as L goes to infinity to the integral of u over R2. This is just Riemann integration. But as we saw here, we do not have a sum over all j in z2 sub L. We have only a sum over visible j in z2 sub L. But this is something that we can handle. And the key point for this is that the density of visible lattice point in z2 sub L is something we can compute. And it is given exactly by 1 over zeta of 2, where zeta is the Riemann zeta function. And this means the following. This means that the relevant of being visible is that we can parameterize n3 unless if n1 is equal to alpha times j, which is visible, then n3 is equal to beta the rotation of the same visible point, if it's perpendicular to m1. Otherwise, you would have more parameters. Okay, where were we? Yes, over here. So this means the following. Okay. So if we take an open set omega in R2, and if you count the number of visible lattice points inside omega, if you divide this number by L squared, then this will converge to the volume of omega over zeta of 2 as L goes to infinity. And this is turned out to be a classical result in analytic number theory that translates into the following coprime equidistribution result. It means that if U is sufficiently nice, say U and its gradient decay in an integrable way, then you can replace a sum over visible lattice point, more precisely L to the minus 2 times the sum over visible lattice points, by 1 over zeta of 2 times the integral of U of z dz. If this was not, there was no restriction over visible lattice points, you wouldn't get this constant factor. And the error that you incur in this approximation is order of log L over L, so this is very nice. This goes to 0 as L goes to infinity. So now that we know how to replace sums over visible lattice points by integrals, of course this lemma is not sufficient by itself, but it carries the heart of the matter. So we can go back to our problem. We can replace this sum by L squared over zeta of 2 times the integral over R2. Those two sums are essentially regular Riemann sums. One of them translates into an integral, and the other gives you a logarithmic factor of L. I will spare you the tedious computation, but tell you what the formal equation that you get for AK. The formal equation for AK is as follows. It's I dt AK. There's a constant which will play the role of our time scale later on. It's the accumulation of all dependencies of L and epsilon that you do in the computation. But the main point is this integral. So it's the integral from minus 1 to 1, the integral over R2, AK plus lambda z, A bar at K plus lambda z plus z perp, A at K plus z perp dz lambda. We'll give the geometric significance of this integral on the next slide. But for now, let us reparameterize time and define the slow time variable tau as follows. T is equal to T star tau. Then formally, at least, the equation specified by AK in the slow time variable is exactly this. We call this equation the CR, the continuous resonant equation, or the CR equation. It's given by I dt g is equal to T of g gt, where T of g gt is given by this integral. So let me give the geometric meaning of this integral. So C is fixed by the right-hand side. This is C plus lambda z. This is C plus z perp. And this is C plus lambda z plus z perp. So what we're doing is that we're taking the function g. C is fixed by the left-hand side of the equation. We are evaluating over those three vertices of the rectangle, and then we are integrating over all rectangles having C as a vertex, and with the weight that is given by this integral, with the particular weight that is given by this integral. Because, I mean, in a rectangle, you have to decide which side is smaller, shorter than the other. It's a symmetry thing. Yeah. Okay. So this equation turned out to be new, even in the physics literature, and it can be regarded as a deterministic analog of the wave kinetic equation. And the main difference between this equation and the Kolmogorov-Zakharov equation, or the wave kinetic equation, is that this equation is Hamiltonian. We have preserved the Hamiltonian structure in the process, and the Hamiltonian is given by this a priori complicated formula. But the first surprise is that this form is not complicated at all. And the Hamiltonian of this equation is nothing but the L4-Strickard's norm on R2. This means that if you want the Hamiltonian of G, all you have to do is apply the linear Schrodinger propagator on R2, raise it to the power 4, and integrate in space and time. Okay, so before I talk about making all this rigorous, I would like to talk about some properties of this equation. Okay, so first, in terms of conserved quantities, yes. So you can change variables, and this you can write this as 1 over 4, the integral over all of R. So you see there are a lot of symmetries in this integral. And then it's a direct computation, four-line computation. Okay, so the following quantities are conserved by the flow of CRs. Of course, the Hamiltonian itself is conserved. The mass is conserved. The momentum is conserved. The position operator. The second moment of the position is also conserved. The kinetic energy is also conserved by itself, and so is the angular momentum. But probably the most surprising conserved quantity that this equation satisfies is the invariance under the Fourier transform. This means that if g of t is a solution of CR, then its Fourier transform is also a solution of g hat of t is also a solution of CR. Moreover, we have that the Hamiltonian function itself is something. It is an invariant under the Fourier transform. Well, if you know that the Hamiltonian, once we realize at the end that the Hamiltonian is the Alford-Sicard's norm, the fact that the Hamiltonian is an invariant function was a remark of Hundor's mark from previous week. Okay. Another surprising symmetry of this equation is that it leaves invariant the eigenspaces of the quantum harmonic oscillator. As we know, so let us recall the quantum harmonic oscillator is the operator minus delta plus x squared, which admits an orthonormal basis of eigenvectors for L2 of R2. The eigenspaces ek have eigenvalue 2k. They are k-dimensional, and they are spanned by the kth order Hermite functions. This will be important when we study NLS with harmonic trapping towards the end of this talk. And the theorem states is that if you start in one of those eigenspaces ek, you will stay in ek for all time. So if g naught is in ek, then g of t is in ek for all time. But I should haste to remark it that this does not mean that the dynamics decouples into finite dimensional ODEs, because if you excite a mode in one eigenspace ek and a mode in another eigenspace ek2, then this will excite everything essentially. You get an infinite system of ODEs. In terms of global well-posedness, the equation has very nice global well-posedness properties. It is globally well-posed in L2. So for any initial data g0 in L2, there exists a unique global solution which is continuous in L2 as well. It's also globally well-posed in HS for any s bigger than or equal to 0. And by the invariance of the Fourier transform, it's globally well-posed in the weighted spaces H0s as well. And a well-posedness result that will be important when we do things rigorously is the well-posedness in the space x sigma, which is the space of functions that decay like x to the minus sigma as x goes to infinity, and this is true for any sigma bigger than 2. The final slide I have on the properties of this equation are on the stationary solutions. Actually, we have a lot of stationary solutions, but I will mention only 2. You might have guessed that the Gaussians will play an important role. So indeed, for any alpha, a complex number satisfying real alpha positive, there exists a constant explicit that we can calculate, c depending on alpha, such that e to the ICT times e to the minus alpha c squared solves CR explicitly. So these can be considered solitons, even in the defocusing case. And these are coherent structures. Applying this symmetry group of the equation, you obtain a 7-dimensional manifold of them, for which you have orbital stability, because essentially they are ground states of the harmonic oscillator. The other important family of special solutions is important because it links the theory of this equation with the Kolmogorov-Zakharov equation, or the wave kinetic equation. So we have that g of t c, which is e to the ICT over absolute value of c solves CR explicitly. And this, if you remember the Rayleigh-Jeans solution of the wave kinetic equation, this corresponds to exactly to n of c equals c to the minus 2. Remember, n is the square of the frequencies, and if you square this, you get the This is exactly the scaling of Gibbs measure. And indeed, we have many other explicit stationary solutions at each energy level of the quantum harmonic oscillator, and we can also write some quasi-periodic solutions. Okay, so these are the only properties that I will talk about concerning this equation. Maybe Pierre, when he comes here, he'll talk about more. But I would like to spend a few slides talking about how to make things rigorous and what does this equation tell us about the dynamics of NLS. So ultimately, what we'd like to do is we would like to project the dynamics of this CR equation, and we have seen that they are quite rich, into that of NLS on a box of size L, where L is finite, or even on the T2 when L is equal to 1. So for this, suppose we have an interesting solution G of Tc of the CR equation on an interval of size interval 0m, and here it is absolutely crucial that we can take m arbitrarily large, so that we can project any long-term dynamics we discover on this CR equation into that of NLS. And so suppose we have such a solution, what we would like to do is we would like to construct a solution of NLS that carries the dynamics of G of T. And to do this, we do the natural thing. We start with solution for NLS that initially at time 0 is given by the same initial data for the CR equation. So AK at 0 is equal to G naught at K. And at later times, we would like to approximate AK at time t by G actually, first you try at time t over t, but actually you realize that you need to compare it at time t over t star, because at some point in the formal derivation, I rescaled time. We had that formally minus I dt ak was 1 over t star t of a. Okay, so, and in order to do that, there are, in order to do that, there are three main difficulties one needs to overcome. The first difficulty is justifying the passage to the resonance system. That was the very first approximation that you have done. And this is usually done by a normal forms transformation, but it is not as simple as one needs to make things very, be careful about making things very quantitative. Well, yes, so and the limit L goes to infinity, the resonance, the almost resonant, well, not everything, but there's not, I mean, if you can have k1 omega bigger than any number, can be bigger than 100. But it can be as small as 1 over L squared if it's not 0. Yeah. Okay, so this normal form transformation, it is essentially a change of variable transformation that allows you to write the equation as the contribution of resonant interactions plus the contribution of non-resonant interactions so that you can treat them as perturbation. And if you do that, it allows you indeed to write this equation for ak as the sum of the resonant interactions plus the contribution of non-resonant interaction, which you can crudely estimate by order of epsilon to the 4 L to the 0 plus. L to the 0 plus means L to the delta for any delta positive. Okay, we'll revisit this problem, this equation in a few seconds. The second difficulty is obtaining good discrete to continuous error estimates, which means effectively making rigorous the passage from sums to integrals that we have done. And this requires some tools from analytic number theory, namely the Mobius inversion formula, essentially the Mobius inversion formula. But the most challenging difficulty, which is not a priori obvious, was obtaining sharp estimates on resonant sums. And this was challenging because it was related to some open sharp periodic Ricard estimates. So let me explain why this difficulty shows up. Yes, please. The time scale t star over here. It's epsilon to the minus 2, L squared over epsilon to the minus 2. Yeah, there's a formula. Okay. Okay, so let me explain why this is something that is very important. If we look at this equation, our whole premise, remember when we derived the CR equation, we threw away those interactions. So our whole premise is that the resonant interactions dominate the dynamics. They dominate the contribution of non-resonant interactions. In order to prove that, you need a very good estimate on resonant interactions. So we need to estimate this sum. So this slide is a completely harmonic analysis slide, if you like. So what we would like is that we would like to take three sequences, AK, BK, and CK. We would like to form the resonant sum out of those three sequences. And we would like to estimate this in some Banach space X, which we have some liberty in choosing, by a constant that depends on L times AK in X, BK in X, and CK in X. Now, the formal argument that allowed us to derive the CR equation tells us an idea of what this constant should be. Of course, we are very interested in the dependence of this constant in L. The formal argument tells us that this constant cannot be any better than L squared log L, because L squared log L is actually achieved if the sequences AK, BK, and CK are actually smooth sequences. They are Lipschitz sequences. The second observation that one can do is that if we decide to work in Sobolev spaces, so we work in L2-based spaces, Sobolev spaces correspond to L2 weighted spaces in Fourier space, then this estimate becomes equivalent, completely equivalent, to the following still open Strickard's estimate on T2. And this estimate reads as follows. You take phi in L2 of T2, you project it onto frequencies less than or equal to n, so this should be T less than or equal to n, and then you apply the linear Schrodinger propagator. You estimate this in L4 space-time, and what you really want to estimate it by a logarithm of n to the power 1 over 4 times the L2 norm. And this estimate was implicit in the works of Bourgain in 93 and 96, but it's still open. And sigma? Where's sigma? Any sigma, even sigma equal 100, you have to answer this. Because at low frequency, when k is less than 1, this is equivalent to this. The weight, you can raise it, or for any sigma, it's equivalent to this. For sigma 0, yes, as well. Yeah. But even if you take I want to emphasize that if you take sigma equal 100, it does not solve this, because when k is less than 1, you find this. Yes. You remember k is in Z2 over L. Okay, so this estimate turned out to be quite difficult, at least for us to prove. So if you are really bent on working on an L2-based space, there's no other way than answering this question. But we have a liberty of choosing this norm x. And if we work in an L-infinity-based space, so if we work on sequences that decay like k to the minus sigma as k goes to infinity, then this estimate becomes slightly more tractable. It's still quite a substantial part of the work, but we can prove it with the sharp constant C of L, which is L squared log L. And here I should pause to point out that it is absolutely crucial that we get the sharp constant. Any loss of any power of log L would kill us here, because either you get the most strong statement you are shooting for, and we were unlucky, or you don't get anything. So here you really need the sharp constant L squared log L. Well, it came from as I said, it came from one way to see it is if you think of AK, BK, and CK as being traces of smooth functions, then if you change this sum into an integral, as we did in the derivation of the CR equation, you get the log L. It's not quite number, it's numerological, I would say. Yeah. Actually, the lower bound that this should be bigger than log N was known. But now that we have this, the corollary that I would like to say is that this proving this estimate in the space X sigma gives you a periodic Strickers estimate at the Stein-Thomas scaling, which up till now we don't have any such estimate. But of course, with this phi2 replaced phi in L2 replaced by phi by a norm that is an interpolation of L1 and L infinity. But the key point is that this norm scales exactly like L2. And this is the crucial part. You want a critical norm that scales exactly like L2 with the sharp constant. It's a scaling. It is a scaling thing. Yeah, but Sobolev embedding is very bad here. Yeah, it gives you too many factors of L. It gives you L to the 4 essentially. Yes. So we knew this. That this is, everyone knew that this is less than n to the epsilon from Bourgain's work, right, for any epsilon. But n to the epsilon would give you L to the 2 plus epsilon over here, which kills you. You really need the exact constant. Okay, maybe if I have time, I'll go a little bit why you really need, you cannot afford any loss there. Okay, so let us go back to our problem. Now that we have a very good way to bound resonant sums, we can go back to our problem, which is estimated this resonant sum in comparison to this. So this is our NLS equation. The sharp estimate on resonant sum, as above, tells us that the resonant interactions are essentially order of epsilon squared log L over L squared. So this is a caricature of the proof. And for those resonant sums to dominate the contribution of non-resonant interactions, all you need is that epsilon squared log L over L squared is bigger than epsilon to the 4L to the 0 plus, which is the bound on the non-resonant interaction. And this gives you the restriction epsilon less than L to the minus 1 minus. And this is called in the physics literature discrete wave turbulence regime. It is exactly the regime where the resonant system dictates the nonlinear dynamics. I will talk a little bit more about this restriction, especially in terms of comparing it with the restriction that we had in this heuristic. But for now, let me explain why you really need the sharp estimate on the Strickers estimate. So if what you would like to do, you'd like to compare AK of t with G at time t over t star. Okay, so we take initial data AK at time 0 to be equal to G at time 0 at k, the trace of EK, and then you define the error, which is the difference between AK at time t minus G at time t over t star. And again, recall that formally we had that the right-hand side of NLS converged to 1 over t star times the right-hand side of the CR equation. So we should compare AK with G at time t over t star. And to do this, the equation satisfied by EK is the following. This is the right-hand side of the NLS equation, and this is the right-hand side of the CR equation. What I will do is that I will add and subtract a resonant sum having its candidates from the solution of the CR equation. Okay, the estimate on this sum is the second difficulty that I talked about, which is making rigorous the passage from discrete sums to the continuous integrals. But it is the first line that I would like to focus on here. And this is the line that will tell us why we need the sharp estimate. Okay. So this is the equation for dt of ak. I have dt of ek, I dt of ek. From this, I have equals to epsilon squared L to the minus 4. The sum over Rk, because I'm subtracting a trilinear term in Ak from G, I will have at least one factor of Ek in it. So I will have Ek1, say, G at K1, or G bar at K2, sorry, G at K3, plus similar terms. Okay, so if I take this in some norm x, dt of Ek, okay, some norm x, and I will use the estimate on the resonant sum that we have. We get this is less than or equal to epsilon squared L to the minus 4. The estimate on the resonant sum tells us this costs us, any resonant sum costs us a factor of L squared log L times Ek in x, and Gk in x is order of 1, plus dot, dot, dot. Okay, so what is this? This is equal to epsilon squared log L over L squared, which is exactly 1 over T star. So what we have is that dt of Ek is less than 1 over T star Ek. Suppose I lost a factor of log L in the resonant sum estimate. I would get a constant over here that is strictly larger than 1 over T star. And as a result, I would get an approximation theorem over an interval that is strictly less than 1 over T star. But T star was the time scale of this function G of T over T star. So for a time scale strictly less than T star, this function does not move. So I would get a void statement. So in the essence is that either you get the sharp estimate over here, or you lose something and you don't get anything. Okay, so this is what I wanted to explain. Okay, so this is the proposition that allows you to go from the resonant sums to the integral, and it relies on some numbers here that I won't go into. But finally, we can state our approximation results. So we fix sigma bigger than 2. And suppose G of Txc is the solution of the CR equation on an interval 0m. Again, m can be taken to be arbitrarily large. This is something that is very important to have the liberty of choosing m. And the only condition we have is on the data such that G naught and its gradient are in x sigma plus 1. Remember, x sigma plus 1 are the functions that decay like x to the minus sigma as x goes to infinity. Again, CR is globally well posed for such initial data. Then if we take L large enough, and if we take epsilon less than L to the minus 1 minus, which was what we called the restriction we had on a few slides ago, the discrete wave turbulence regime. If we take Ak of T to be the solution of NLS, such that at time 0, Ak at 0 is given by G naught at K, then at later times, we can approximate Ak at time T by the function G at time T over T star at K in the space x sigma by a constant over log L, so it improves, it goes to 0 as L goes to infinity. And the key point is that the time interval of this approximation allows us to project all the dynamics of G on the interval 0m into that of NLS. And the reason for that is that if you evaluate this, if you apply this inequality at the endpoint of this time interval, which is m capital T star, you are evaluating G at capital M, which means that you have projected all the dynamics of G on the interval 0m into that of NLS on a box of size L for L large enough. Well, we have also an approximation theorem on T2, which comes just by rescaling. On T2, one has to understand the CR equation as an equation for the frequency envelopes of the solution. This means that we are looking at, okay, I lost my chalk. Oh. Hope I did not break it. Okay, so this means that we are considering solutions for NLS that are initially given by, or at any time are given by v hat at k, which is the frequency, the Fourier transform of the solution, is given by essentially a function of k over n times some normalizing factor. So if this happens, we say that G is the frequency envelope of V. Okay, so what we will have is that we'll take G that is such that G naught and its gradient are xs plus 3. Again, CR is globally well posed for such data. Then if the frequency scale is large enough, and if we take V of t to be the solution of NLS, whose initial data is given by a normalizing factor times G naught at k over n. So at time 0, the frequency envelope of V hat is given by G naught. This normalizing factor is chosen exactly to make V has size 1 in HS, uniformly in N. Then at later times, you can approximate the solution, NLS solution V, with the solution whose frequency envelope is given by the solution of the CR equation at time t over t naught. T naught is the time scale in this case. And by a constant over log n, so this goes to 0 as n goes to infinity. And the key point, again, is that the time interval of approximation is long enough to observe any interesting dynamics of G. So if you evaluate G at time, if you evaluate this inequality at time t naught m, then you are evaluating G at capital M, which means that you have projected all the nonlinear dynamics of G on the interval 0m into that of NLS on T2. And using this, using this theorem, one gets many explicit examples of coherent out-of-equilibrium dynamics of NLS on T2 using the special solutions we have for the CR equation. And then this gets me to the following remark, which I would like to explain. So we started the motivating the large box limit by saying that if epsilon was less than, we started by motivating the large box approximation by saying that if L is bigger than epsilon to the minus 2, then NLS on R2 is your large box approach, is the right equation to look at. And the theorem 2 slides ago, it tells you that if epsilon is less than L to the minus 1 minus, then the CR equation is the equation to look at. Okay, so this means that epsilon is less than L to the minus 1 half. But this leaves us with the regime L to the minus 1 minus epsilon less than, L to the minus 1 minus less than epsilon less than L to the minus 1 half, where we still do not know what's going on. And it would be very interesting to know what is the right effective equation in this region. Okay, so this is very much, and you can do this for other equations. For example, up to now we have done it we already finished doing it for the 1D quintic NLS with correlation with Chata, and all the structure and symmetries persist in this case. Okay, so in the remaining 5 minutes, I would like to talk about one extra property of this equation, which makes it quite relevant in studying NLS with harmonic trapping. So as we said, we are interested in confinements that are either geometric confinements from the box or confinements by a potential. And this is the most well-known instance of a confinement by potential. It's a very important model in Bose-Einstein condensates. When you study NLS, we replace the delta by minus delta plus x squared. This is a harmonic trapping. And if we want to understand the long-time behavior, we'll do as Nikolai did, and as we have always done, we conjugate by the linear flow. So we define the profile f of t to be e to the minus ith u. Then the equation satisfied by f is this compact equation. I dt is f is equal to e to the minus ith multiply e to the ith f squared e to the ith f. Then we go to the frequency formulation. We will expand f in terms as a sum of fp, where fp is the projection of f on the pth eigenspace of the harmonic oscillator h. And if we do that, just by expanding this sum, we get that the equation satisfied by fp is given by I dt fp, the projection on the pth eigenspace, and then you have a sum over p1, p2, p3 in n, e to the I lambda p1 minus lambda p2 plus lambda p3 minus lambda pt times fp1, fp2 bar fp3. This is exactly this equation in Fourier space. As we said, as we already have experienced, resonant interactions play a particularly important role in this case. So let us isolate the resonant system. The resonant system corresponds exactly to the system for which lambda p1 minus lambda p2 plus lambda p3 minus lambda p is equal to 0. And it's given by the following system. I dt f is equal to r f f f, where r f f f is given by exactly the previous sum, except that you're restricted on lambda p1 minus lambda p2 plus lambda p3 is equal to lambda p. in order to observe the Hamiltonian structure of this equation, we will rewrite R as follows. So I will replace this sum over lambda p1 minus lambda p2 plus lambda p3 is equal to lambda p over the sum over all p's, except that I will introduce an artificial integral, which is the integral from minus pi over 4 e to the I lambda p1 minus lambda p2 plus lambda p3 minus lambda p. Since this is a multiple of 4, this vanishes unless this vanishes. And now I can redistribute each lambda p1 with fp1, etc., and rewrite this integral as the integral from minus pi over 4 to pi over 4, e to the minus I tau h, e to the I tau h f, f bar, e to the I tau h f, d tau. And this, I can observe it as the dq by df bar, so it's where q is the Hamiltonian of this equation, and the Hamiltonian is given by the following L4 Striker's norm, except that you have an h over here, not delta. So we're starting to see some similarities with the CR equation. In order to see the full similarity, we use the Lens transform. The Lens transform gives you a relation between the solution of the free Schroedinger equation and the solution of the Schroedinger equation with harmonic trapping. And it tells you that this is the relation. If u is the e to the it delta phi and v is e to the it h phi, then u and v are related by this equation. Then if you plug this formula into the previous formula for q, you notice that everything magically cancels, and you get that the L4 Striker's norm with h is the same as the L4 Striker's norm with delta, and this is exactly the Hamiltonian of the CR equation. So we get the following theorem, which was in collaboration with Laurent-Thomas, is that the CR equation, which we initially derived as the large box limit of the resonance system for the homogeneous analysis equation, is exactly the resonance system for analysis with harmonic trapping. And this begs the question whether CR has any universality properties as a model for resonance system for cubic analysis in 2D. And for this, one needs to answer before we make a conjecture. One needs to get some more vocabulary of such resonance systems. For example, what is the infinite volume limit or high frequency limit of NLS on S2? Okay, and then once you have this, you can observe CR as an asymptotic system, not as a long time system as well. But this is done by doing the same trick that Nikolai told us, is to consider NLS with partial harmonic trapping. So we consider IDTU plus H partial trapping, which is given by minus delta plus, but you only trap in 2 directions. Okay, and it turned out this is called a cigar-shaped trap, and it's of utmost importance at the basis of theoretical explanation of some important experimental observations of Bose-Einstein condensates. And we have the same theorems that Nikolai said, actually following the same proof that we did with Benoit, Nikolai, and Nicola. We have the following theorem. There exists an epsilon such that if u naught is smaller than epsilon in some Banach space S containing Hn, and if u of t is the solution of this NLS with partial harmonic trapping with initial data u naught, then u of t exhibits modified scattering to the Lesson dynamics of CR in the following sense. This means that there exists a solution g of t of CR such that the profile of u, or e to the minus it h u, converges to g at time phi log t. Here I put 2 quotations around CR because you have to add the parameter xi, which plays no role in as was the case for us when we studied R cross TD. And we also have okay, so this is a signal that I'm out of time. We also have the modified scattering operator construction. Any solution of the CR equation can be realized as the limit as t goes to infinity or solution for NS with partial harmonic trapping. And this gives you another independent justification of the CR equation as an asymptotic system, not as a system that describes long-term dynamics. And we use also the special solution of CR to give interesting non-scattering asymptotic behaviors of analysis with partial harmonic trappings. And one key point that was also a surprise for us is that these solutions allow us to justify an important approximation done by physicists, which they call the quasi-1D approximation, that allows them to reduce from the 3D dynamics of analysis with harmonic trapping to the 1D dynamics of the completely integrable cubic analysis with all its plethora of interesting solutions. And this is based on a multiple time scale expansion by taking this ansatz. And our theorem justifies it rigorously. And more importantly, it gives the right extension of this approximation when higher energy levels of the quantum harmonic oscillator are excited. Notice that this ansatz is based by taking the ground state of the harmonic oscillator. It's called the ground state vortex. But you can excite vortices of higher degree. Okay, so the last slide is that conclusion and one question is that we started with NLS on a box of size L in the weakly nonlinear regime. So where we were able to approximate NLS by its resonance system. And we derived the equation, a new equation, the large box limit L goes to infinity. The obtained equation, which we called CR, turned out to satisfy many interesting symmetries and stationary solutions. And then we proved that any long-term dynamics of the CR equation can be projected into the long-term dynamics of NLS on a box of size L if L is sufficiently large and the size of the data is small enough. Equivalently, we also saw that any long-term dynamics of CR could be projected on the dynamics of NLS on T2 by understanding CR as the equation for the high-frequency envelopes. And then we realized also that CR is the resonance system for NLS with harmonic trapping, and which allowed us to observe it as an asymptotic system, not only as a long-time system. And the final question is, which I think is very interesting, is whether we can construct solutions of CR whose norms grow in time. I think this question is very interesting, not only because it would give us an analog of the result that Nikolai told us about, but because of our approximation theorem, a positive answer to this question would give a reproof that Colliander gives the Sapinani Takawaka and Tau result. And it would give you a proof that NLS with harmonic trapping exhibits large but finite growth with full trapping and infinite growth with partial trapping. So I think this is a very interesting problem that we are very interested in at this point. So thanks for your attention. Yes. So we have not done this. I have not done the computation completely, but I suspect you get the same equation by just approximating the irrationality coefficient by Dirichlet's theorem by rational. Because for rational tori, you would converge to the same equation, and for irrational tori, you have to just follow the numerology very carefully. That if you approximate the irrationality coefficient theta by minus using Dirichlet's theorem by 1 over, say, 1 over L to some power, maybe 100Q, say, then this would give you, on the time scales that you're interested in, this would give you the same equation. If you are able to do that, then you get the same equation. Well, if you approximate by a rational torus, then you start, you are able to use the number, same type of number. I mean, in the end, visibility is so. These are how you solve a system of Diophantine equation, a linear system of Diophantine equations.
So this is what you've been working for Sherman? When was this?
This was last year, in September. We put it on archive.
Oh, last year.
Yeah.
Have you been working recently?
Yes. Well, we are continuing a lot of things with him and Laurent on this and rewriting it for other equations as well. And yeah, so there is in this direction we are continuing quite a few things. And we're also doing something on the derivation of the Kolmogorov-Zakharov equation. I think we have, if we add some type of forcing, we are able to get the derivation of that equation. Without any type of forcing, this is a very, very hard problem.
Okay.
Yeah.
Very nice.
Thank you.
That's a very nice talk.
Oh, thank you. No, I think we can do so we can do something else in one. Yes, we are